Alrighty, ladies and gentlemen, we're now on to section 9.3, geometric sequences and series. Here we're going to be finding the nth terms of geometric sequences, partial sums of geometric series, and find sums of infinite geometric series. Alright, so first of all, what's a geometric sequence? Well, it's a sequence where the ratio, or if you'd like quotient, the ratio of consecutive terms are equal. That ratio is called it's a common difference for arithmetic, so it's a common ratio for the geometric guys, and D for difference, so we're going to go with R for ratio. Alright, now assuming a geometric sequence, what are the next three terms of the following sequence? Well, again, if this is a geometric, okay, we have to be basically multiplying consecutively to get from one term to the next. So for 2 to 6, this is times 3. That's a little x right there for times. Okay, so basically I just have to keep multiplying by 3. 6 times 3 is 18. 18 times 3 is 54. And then 54 times 3 is 162. Alright, so it looks a lot different from a arithmetic sequence, because quite honestly they just get a lot bigger, a lot faster, as long as you're multiplying by the right number. Alright, now to get to the nth term of a geometric sequence, okay, I'm going to capitalize on the previous example we just did, but here we go. A sub 1 equals 2. Well, that was taking the original term 2 and using the common ratio, 0 times. So that's still 1 to 2. Well, the 6, we use 2, and then we use the 3 just once. And then to get to the 18, we use the 2, but then we ended up using the 3 twice to get that far. Alright, using the 3 times got me to 54 from the 2, and likewise the 162, I needed to use it 4 times. Okay, hopefully you notice the difference between the subscript and the exponent we're using here. So the formula for the nth term is a sub n equals, again, basically look what happened there. We took the first term times the common ratio, and then we used whatever term we were on minus 1 as the exponent. So basically there's your formula for the nth term. Make a nice pretty box around that. Alright, there you go. Let's move on from there. Alright, so like with some of the other things we've used, if I want an expression for the nth term of a geometric sequence, and it gives a little bit of starting information right there. Okay, well this one's going to be pretty cut and dry, because the nth term gives me, again, our starting times r to the n minus 1, so in our case, a to the n equals, our first term is 16, and then our ratio is 1/4. Just be careful to use proper parentheses when necessary to make sure you're showing the various groupings that are going on. And n minus 1. Okay, if you want to get crazy, you could start playing around with exponent rules and clean that thing up a little bit. But quite honestly, as far as I'm concerned, that is a fantastic nth term formula. Alright, and that formula is good in case you want a particular term in a sequence. So finding the 12th term of a geometric sequence. Okay, well, first thing I need to do is find my first term. Well, there it is, 1/2. Yay! And what I also need to know is my r. Okay, so again, basically it's what I'm multiplying to get from one term to the next. And again, with the fractions, maybe it's not very obvious, but let's move to the whole number segment right here. To get from -1 to a 2, that's times -2, and then from 2 to -4, that's also times -2. So I'm feeling pretty good about that. And yes, easy enough. If I do take 1/2 times -2, I certainly do get -1, so that kind of verifies it. Okay, if that's not something you can do in your head, again, it's called a ratio, so all you do is take one term and divide it by the previous term. So what we could have done to get r is take the -4 over the 2, or again 2 over -1, etc., and work that out as a -2, and you could have got it that way. Okay, but now going to my formula, a sub 12, because again I want the 12th term, is going to equal, again, the first term, which in this case is 1/2, and that's going to be multiplied by my r, -2, to the 12th minus 1 power. So effectively that's 11th. Typing that thing in my calculator gets me an answer of -1024. Alright, to get the partial sum of a geometric series, which basically in partial sum means you don't do the whole list, so we're talking about a finite list of numbers here, so that's what I'm saying there. Alright, now, again, you don't need to write this down, but I think it's kind of neat to see where the formulas come from sometimes, and here we go. Alright, so if I have a series, again, geometric, so I start with my first term and then I start multiplying by various powers of r. Okay, it's always one less than the total number of terms though, so that's why it goes over here to n minus 1. Okay, n minus 2 because I'm a little bit before there. Okay, and that's going to equal s for my sum. Okay, now if we multiply both sides by r, okay, notice basically each term now the exponent for r just got bigger by 1. And I get all these guys. And then notice it's r times s now. Okay, now here's where it gets kind of interesting. If I'm going to subtract the second equation from the first, okay, I'm doing a sub 1 minus nothing, so that's a sub 1 because there's no like terms. But then notice what happens after that. I've got a1r and then a1r. So those two guys are going to cancel. AR squared, etc. And then all these other little terms are going to cancel all the way through, except for this guy here, because I didn't have a matching term on top. Okay, but again, I'm subtracting, so it actually works out to be a minus a sub 1 r to the n. Okay, likewise, I'm subtracting here on the right-hand side, so I get the s from the first equation minus the rs from the second. Alright, now I can do a little factoring, as it says right here. I can factor out an a sub 1, and it leaves me with 1 minus r to the n. Likewise, on the right-hand side here, I can factor out the s, and it leaves me with a 1 minus r. Okay, now dividing each side by the 1 minus r, hint. Alright, we're going to get something that I'm going to write on the next page. Alright, so here it is, the official formula, after doing that manipulation on the previous page. The sum of the first n terms of a geometric series is the first term times that 1 minus r to the n power that we had, and then remember we divided through by 1 minus r. Okay, that is an n right there. Okay, be careful of your handwriting. Sometimes an r and an n might look similar depending on your handwriting, so make sure this is an n as the exponent and the other two guys are r's. Okay, but basically that will calculate the sum of any number of a finite geometric series. So for instance, we've got this right here. Alright, I've got the from 1 to 6 of negative 512 to 1/4 to the n. So again, to use this formula, I need to know my first term and my ratio and the number of terms I'm going to use. Okay, so my a sub 1 equals, again, don't assume it's the 512. So it's negative 512 times 1/4. And again, the first number I plug in is a 1, so the n becomes a 1. And 512 times 1/4 is going to be a negative 128. So there's actually my a sub 1. Okay, the other thing I need is an r. Okay, hopefully from the sigma notation that's fairly obvious. The 1/4 is the thing that we're going to continue to multiply by. Alright, and then from there I need the number of terms, and if I start at 1 and go up to 6, that tells me I have 6 terms. Alright, so there's all the vital information I need. So the sum of those 6 terms, which admittedly wouldn't be too much trouble to kind of just calculate all 6 of them individually and add them up, but for the sake of using the formula here, I've got a negative 128, and then 1 minus, and here's where it gets a little dicey. Be careful because you've got a fraction that you need to throw an exponent on, so maybe you want to have a parenthesis inside a parenthesis to kind of help things show nicely. And on the bottom I'm going to have my 1 minus 1/4. Okay, from there we're going to have to type things in the calculator. And my calculator is kind enough to tell me negative 170.625, or if you'd prefer, as a fraction, that works out to be, brace yourself, negative 1,365 over 8. I will accept either one of those, depending on whichever one you like better. Alright, now there's something about this example that tends to mess people up, and it's not the fact that I have a little typo in here that's supposed to be a k, it's an n on the notes if you printed them out. Alright, so again, the 3 bits of information I need are the first term, so a sub 1. Again, I also need to know the r, common ratio, and I need to know the number of terms. Okay, so again, the a sub 1, okay, now hopefully you actually don't have to do this, you can just look at the numbers and figure it out in your head, but for the sake of argument here, that's going to be 20 times the negative 1/2, and again the first value I'm going to use is a 0, so I replace the k with a 0. Okay, and of course anything to 0 power is 1, so effectively that cancels out and leaves you just with a 20. Okay, the r, again, just thing in parentheses, so negative 1/2, and then the n, if I'm starting at 0 and going up to 6, that does have 7 terms in it. Okay, so again, that's one of those things that people tend to put a 6 right there, and of course that throws things off. Alright, but that being said, the sum of those 7 terms is going to be, again, the first one, 20, and then again, careful with the 1 minus negatives and fractions altogether, that does get a little bit messy. if you're not careful about things. So negative 1/2 to the n, so of course that's a 7. Alright, and then we're dividing by 1 minus r, so 1 minus negative 1/2, so again, be careful with that. Alright, again, punching all that in my calculator, or doing whatever you need to do to clean it up a little bit first before you type it in, whatever works for you. You should get 13.4375, which granted is a little bit messy. So if you prefer a nicer looking fraction answer, that works out to be 215/16. Again, whichever one of those is better for you, I'll be happy to take. Alright, let's move on to the sum of an infinite geometric series. Okay, now, my personal opinion, I think this is fun. But here you go. I'm going to be able to add up an infinite number of things. Well, here we go. So 4 plus 8 is 12, plus 16 would be 28, plus 32 would be 60, and then of course the next term here would be 64. So I'm over 100 right now, and if I keep going, these numbers are going to get bigger and bigger, so of course my sum is going to get bigger and bigger. So really, infinity is the sum for that, as the numbers keep getting bigger and bigger and bigger, okay, which does present a problem for us, and we're going to talk about that on the next slide. Alright, so for the sum to be found, okay, having a ratio bigger than 1, like we did in the last example, the numbers started getting really, really big, really fast, and then, you have a sum of infinity. So that doesn't really work very well for us. But if we have that ratio being less than 1, and I'm going to clarify that a little bit better in a second. Alright, actually, the absolute value of r needs to be less than 1, because basically I could have the numbers change from positive and negative going back and forth, and that'd be just fine. So that's kind of what we're saying here. So as long as the absolute value is less than 1, the numbers are going to get smaller as we continue down the list, and then it's going to allow us to kind of add them all together, because as you're adding smaller and smaller bits, well, they kind of fall in line, but we'll get to that in a second. Okay, so if that absolute value is less than 1, okay, what does r to the n effectively equal as r approaches infinity? And if you're not sure about that, I recommend picking something less than 1, plugging in your calculator, and raising it to a fairly high power. For instance, let's just take something simple like 1/2. If I take 1/2 and I, let's say, raise that to something reasonable like a 50th power, just to not get too out of control. So that's an exponent thing right there, in case it was a little too sloppy. Alright, it gives me something about 8.88 times 10 to the negative 16th power, okay, which is an itty-bitty teeny tiny number. Okay, of course that's not infinity yet, that's a far cry from infinity, it's only 50. So hopefully you can kind of imagine there, this guy effectively equals 0 as I start punching in really, really, really enormous numbers. In fact, your calculator probably will actually spit out 0 if you put in a big enough number as far as the exponent goes. Alright, but what that allows us to be able to do is to take our previous formula right here and do a little bit of adjusting. So I want the sum of an infinite number of terms. So I'm going to take that a sub 1 and I'm going to multiply it times 1 minus r to the n, but remember r to the n is effectively a 0. Alright, divided by 1 minus r. Well, that gives me a sub 1 times 1 minus 0, which is kind of a silly thing to write, over 1 minus r, and then that gives me the formula we have on the next page. Alright, so for an infinite geometric series, with the absolute of r being less than 1, that's an important characteristic that we have to go by here. Okay, again, that numerator basically is just like having a sub 1, and the denominator is just 1 minus r. Okay, so what I love about this is you're adding up an infinite number of things, and it takes a very, very, very simple formula to get that done. Alright, so basically, now to use this formula for a problem here, alright, to do this, again, I need to know only two things. I need to know my first term, which my first term is, again, just taking that 24, and then 1/3 to whatever the appropriate power is, in this case, 1, because again, that's my starting value down there. Alright, and 24 times a third is an 8. And I don't care about n because n's infinity. Okay, but I do care about r. Alright, and r in this case again is the 1/3. So all you have to do is put in that numerator as your first term, and then 1 minus whatever that ratio is, punch a few buttons, or hopefully you could handle doing that in your head, but I'll leave you alone as far as that goes. And that works out to be 12. So, I don't know, to me that just seems incredible. You can add up an infinite number of things and just get a whole number answer. I'd be happy to explain that more in class, but I don't make the video too much longer than it has to be. So there it is. Questions, comments, concerns, of course. Make sure you ask me in class. See ya.